Okay, hello everyone. Maybe let's start. I'm glad to see so many of you today. Welcome, and I hope together with Frank, with Errol, and the entire Picterra team, I hope you are all healthy and safe. And welcome to our webinar about artificial intelligence in urban planning and city management. And I will pass a microphone to Frank, our CTO, now. If you want to ask any questions, we have chat here on Zoom. So you are welcome to ask questions. We will have a Q&A session after the presentation. Thanks.
Thanks, Monica. Thanks. Welcome, everyone. Very happy to have you all there. First webinar of this year, a bit in special conditions, and but that's the perfect setup, everyone remote to do it. So just to recall to everyone, so we are Picterra, so a company based here in Switzerland, nearby Lausanne, and we started to develop our technology 4 years ago. And so it is basically a geospatial platform where you can train deep learning detectors very quickly without any line of code. And the idea there is that you can basically bring in just few training examples and you will start to iterate, improve your detector, and then deploy them at scale. We'll talk a bit about this later, and you will really see it in the live demo after. But so really we provide an infrastructure, and a complete infrastructure, and then can be really used without previous experience nor coding. So the agenda, so first there will be a role that will bring in the context and an example around urban planning and city management. And then I will walk you through a little bit the different Earth observation platform that can be exploited in that context, and show you basically applications and opportunities in that context, and show you live and different examples on the platform. And we'll finish, as Monica said, with some questions and answer. We'll see with the time, but we'll have a few minutes for that. And anyway, afterwards, we'll follow up with some further answers to the different questions that will be provided. So happy to pass the talk to Errol. So Errol is mute. Monica, if you can unmute him, that's...
Yeah, just a second.
There we go. Hello, everyone. I do apologise for the circumstances. I'm sure everyone's doing well, and in an ideal world, we'd love to meet all of you guys individually, I'm sure. But this is what it is. This is how the world is at the moment. So the way we want to sort of talk about the issues here are to lay out the general context of why and how AI helps in urban planning, in city management, in those things that you know, we take for granted quite often. And obviously combined with the right data, it can be an incredibly powerful tool. And cities in and of themselves are massively complex entities. I mean, we could spend weeks just discussing, you know, the complexities of cities over time. But basically stripped right down to the core essentials, they're people and communities that interact with objects. And those objects are roads and buildings and, you know, other objects across a broad range of settings and contexts. And if we think of those objects as assets, then it's, you know, it's only sensible, it's only sound management to ensure that you're looking after them, managing them correctly, so that you minimize the downtime of those assets, you increase their performance and their life expectancy, and that should, you know, in an ideal world, translate into higher performance. So you get more from those assets for the cost. We lower the cost going forwards, and you end up with happier users and better sustainability of those assets. So, you know, but we can break that down into other issues. For example, if we're going to make asset management an issue, then proactive maintenance, make sure that we're ahead of the game. Make sure that we're looking at the right issues at the right time. So we prioritize all of those different asset maintenance programs to be the most urgent first. We look at the condition. We need to know what's going on the ground. So we look at damage. We look at roads. We look at wear and tear. We look at the power lines. We look at the buildings themselves and their footprints, and the entire raft of different asset types. We try and minimise those areas where we have blind spots and we can't see what's going on. So we used a vast array of different types of data to try and assess what's going on the ground. And what we're trying to reach is something called maintenance cost optimization. And I'll spend a couple of seconds on that coming back in a minute. So, so basically, in order to really sort of manage the maintenance, we need to get the right budgets in place for each of those programs. And it's crucial, therefore, you can't just do this off the top of your head. You have to establish a process. That what damage am I looking for? What types of damage? How do I classify that? And how do I prioritize it? So, things like, again, coming back to roads as an example, because that's something we all interact with every day. Cracking, surface cracking, potholes, subsidence, surface erosion. These are quite often indicators that something really desperately urgent needs to be put into place. Otherwise, it's going to get worse and the costs will subsequently increase by the time you actually get round to doing something about it. The other thing is that, obviously it's an incredibly resource-intensive process, looking after all of this. So, there's a lot of labour in terms of, most of the time with road management, it's manual surveying. It's a man in a van with a stick driving along the road and stopping every time he sees a crack and putting a stick in it and trying to work out if it was deeper or wider than the last time he did it. You've got to map all of that. You've got to bring all of that information back. You've got to build databases. It's an incredibly, tiresome and labor-intensive process. You've got to look at complex project planning to allow the man in the van to do what he's doing without, problems. And we've got to make sure that those valuable and scarce resources aren't mismanaged and that those budgets are used in the most appropriate and efficient way, because, otherwise it becomes a mess. And then, of course, there's all the other assets. I've used roads as an example, but you've got to do the same thing with buildings. You've got to do the same thing with all of those utility structures that sort of drift into the background, like, power transformers, pylons for microwave towers for your mobile phones, phone line poles, rails. Gasometers is a peculiarly UK thing. I don't know if you guys know what a gasometer is. It's just a big storage tank for liquid gas, and pumping stations. And the end result of any type of monitoring, any aspect of a monitoring program, is that what you're trying to do is you're trying to assess if those assets are in desperate need of attention. You're trying to get to the point where the lowest cost to find that optimum failure rate over time is found, so that you can plan exactly when you're going to use the assets, and you've got time to dedicate those assets to that issue. And that's what we mean by maintenance cost optimization. And, to give you an example, going back to the roads for a second, there was a program, Cornell in New York, had a program called the Local Roads Program, and they found that the average cost to look after 1 mile of road a year in New York is around $10,500, up to $10,500. And there's an annual highways report that comes out every year in the US, where I think they estimated last time I saw it, that there was $420 billion worth of backlog to maintenance. So if you don't get on top of this stuff, it becomes a bigger and bigger problem. So to use a very specific example, we did some work in the US, in the state of Indiana, where we were asked to contribute to a program to allow the city council to manage this road maintenance preemptively. To use our platform and drone footage to map all of those areas where we felt that, or they felt that remedial attention was required urgently, so they could map how to spend that public money, and then use that as a blueprint for all future infrastructure maintenance. so that you don't have to keep repeating the same program over and over and over again. And we went through a workflow. So the workflow is the data acquisition is done by the drone pilots. They generate a series of ortho photos, which are then used by our platform to find and prioritize those areas of maintenance. And later on, Frank will show you exactly the type of outputs that produces. And what we can then do is you can then use that to answer the question. Where do I need to put the money, and when do I need to do that, and how much of it do I need to put? And that project, and I use this as a very stark contrast in what happens when you use AI and the right data, is that the total cost of that program for that particular city was $2,400. It took 2 people, 1 drone pilot, 1 experienced road engineer. It took 5 days of work to do that project, including just 8 hours to build the detector, to load the information, to map the results, and to output the reports. And after that, what happens is that you end up with a $1 per day labor and hardware cost, and it was $350 a day. And in very stark contrast, if they'd done that program the way they'd always been doing it, the very same program would have cost $64,000. It would have involved at least 20 people with various different disciplines. It would have required at least 2 months' work because it would have all been a manual process to find and identify and prioritize that damage. And therefore, that works out at $1,600 a day. So the difference is immense. And I hope that what that one example gives you is an understanding that with the right type of learning, with the right type of platform that teaches, that learns from the information you give it, you can then replicate that across multiple different scenarios, and you've got a blueprint for how to find and track that sort of damage. So I really hope that's been of use. I'm now going to hand you back to Frank, and who's going to go into a lot more detail. But please do follow up with any questions at all, and I'd be happy to answer those. So thank you very much indeed.
Thanks, Errol. Very nice. I think that also this concrete example can really bring a clear idea of the type of benefits. Now getting into basically the Earth observation part and which data can we use for such type of project. This is where basically we have quite the choice. But first thing I would like to make clear, and I mean, here it's about, we're generally talking about machine learning AI in the context of city management and urban planning. First thing I want to clarify is that there's different steps where machine learning can play a role. And so you have basically this, let's say, three steps. So the first one is using machine learning AI to extract information from imagery, so to produce geospatial information that can then be used in GIS softwares. Then the second stage is that once you have these geospatial information and patterns, you can try to analyze them and see a little bit the relationship, the spatio-temporal relationships between them. And there you can also use machine learning in order to do that. Finally, if on those geospatial data you have some metadata, some attribute that comes and enrich those data, you can imagine, for instance, that you have mapped all the bus stops on a city, that you have attached to that all the timetables, and you can start to do some further analysis on transportation, for instance. So you see that there's really this first level of first producing this geospatial information into which then you will start to be able to dig further into analysis. So today we are definitely at the first stage, and we will investigate how we can extract this information from imagery. But of course, good to keep in mind that then machine learning and AI can really apply further along the chain. So in terms of platform to acquire Earth observation imagery, there's quite a choice. I mean, ranging from low resolution satellites at 10 meters, which are free, up to the airplanes or the drones. And what will drive a little bit the choice there is, of course, what do we need to monitor, basically, and so the resolution needed. Knowing that with the satellite, you'll be able to come up to 30 centimeter, then at higher resolution than this, you'll have to jump to the airplanes or the drones to go up to even millimeter resolutions. Something that is coming, and we'll have to see what it will mean in terms of costs, coverage, resolution, but there will be high altitude platforms. These platforms will be typically in the form of solar drones or zeppelins that will be in the stratosphere region, and they will cover a certain region, typically the scale of a state, for instance, something like that. And they might be very interesting in terms of having near real-time data at lower cost. How to get the data? That's something quite key. I mean, when we start to want to investigate into extracting information, the first thing to do is to check if there is any information, any data available. We've put it together now on a website. This basically this imagery portal. So I'll just show you. That looks like that. So basically, you have now these different available imagery. So we just started off, so there's some countries there, but it's good to check anyway before you start to see what's available. There's also the Open Aerial Map portal where people are putting their aerial drone imagery, and so you can check over your area of interest. And if you need to buy even new imagery, new satellite imagery, you can actually use our partner here, Skywatch, to directly order some new imagery. If basically you have already imagery, so you may have access to some campaigns that have been done, for instance, aerial campaigns. You may have bought some satellite imagery already in forms of GOTs, for instance, or you may even have run your drone orthomosaics. You can actually bring all that on the platform, on Picterra platform, to start and build your detector without any trouble. You may be even running a server, a web map server, ArcGIS server or a Joe server. These can also very nicely be plugged, you will see in the live demo, to the platform. So then you don't have to bother about any upload of data. Just to mention that here, Metashape, for instance, which is a photogrammetry software, has an option to directly push data to our platform. So you can directly upload your orthomosaic from the Metashape software. So regarding the data, what you have to have in mind is that you're not limited to visible color imagery. What you can bring and build a detector on top are really various. So you can have false color imagery with near infrared. You can have thermal imagery, which can be interesting for seeing defects in solar panels, for instance. You can even bring radar imagery. So there, the only thing is that it needs to be 3 channels so that you can visualize it then in the browser and you can start to build your model by looking at your image. As I said, so the access to the free satellite data at 10 meters is directly possible inside the platform. We'll also show this in the demo. So the platform is there to really put aside for you all the keeping up with the latest machine learning frameworks, keeping up with the latest type of models and architecture. So this is what we take care of. And you can really concentrate then on building and improving your model. So this machine learning part of the technology and the infrastructure is really transparent and you don't have to bother about it. In the end, just want to emphasize there that it's really the idea that you interact with the model. So when you're building your deep learning models, you are basically getting feedback from it and you can quickly iterate. So you will see this also in the demo, the way you can very quickly iterate through what you are building and what the model asks you to correct. So once you get some output and the detections from the platform, that's not the end. So from there, you can basically bring back this data to your GIS softwares. So you may be using ArcGIS, QGIS, and other software like that. So of course, all the data that is output is geospatial data that can be directly imported there. You can bring that also in third-party software like Tableau for doing very nice visualization, as you see on the right. Otherwise, inside the platform, you have, of course, access to some statistics. You can also do some export in PDF. So there is the rough elements are there, but the idea is that you can really continue after and plug this inside your workflow. So now let's have a look at applications and different opportunities in this context. So what I wanted to just first make clear before we dig further in the context of city management and urban planning, the platform is very flexible. So that was just to show you that it's very diverse what can be done on the platform. It's not limited to that specific topic and that type of applications. It ranges from agriculture, forestry, to all the urban elements, of course, but there's not really a limitation. So bringing imagery data, then you can really start to extract any information you're looking at. When we look more closely to urban and road features, everything you want to have to enrich a cadastre of a city. These are the type of things that have been done on the Picterra platform. It's not exhaustive, but that gives you a little bit of a feeling of the range. I mean, from the macro elements like buildings, like cars, vehicles, of course, parking lots, to something a little bit more fine-grained, what you will find on roofs, for instance, solar panels, chimneys, air conditioners. So that's really there. You see, you have all these different levels that you can deal with. Of course, when you're looking at these different features, you may be more interested in really localizing some of them. So you can see here, for instance, you have some speed sensors on railways. These are really localization. But you have here also building footprints, and you have there really the segmentation, so the mapping part that is recovered. You see you have actually two colors of buildings that are telling about a different stage of construction. The same when you look, for instance, at the parking lot. You may want to look at vehicles, but maybe you want to really just map the parking space or different type of parking space. Maybe you want to map any handicapped parking spots. So there's really this adaptation to what you need to extract. Looking at road, as Errol presented before, so when you want to assess the conditions of a road, there's really different things you want to extract. The first natural one is really to map the cracks, the alligator cracks. So there it's really a segmentation problem, and you can build a detector to do so. So you see here an extract. But then in order to be more precise in the way to characterize the road segment, you want to have the intersection of cracks. So if you see here on the bottom right, the small red dots are basically intersections that have been detected. So you can really build different detectors for these elements. You can then do a dedicated one for potholes, and then it's not ending. So you could continue to dig further and categorize different further type of damages on the road. Another typical element found in cities are actually graveyards, and they are often lacking of mapping in the cadastre. And this is something that we had often a request and discussion about, is how can we map basically the graveyards, and how can we detect and change from time to time by doing regular surveys. So there you can pretty easily do that. So actually doing the mapping of the graveyard, giving some examples, you end up with an output like that. So I have it, no, oops, I will reload it. So you can do it on the different surveys, and then simply in your GIS, you could compare the 2 dates and spot where things have changed. So looking back at it, okay, I will bring it after. So another point is solar panels. Of course, you may want to spot the solar panels for different reasons, but one can be to try to estimate the amount of sustainable energy you have in a certain neighborhood, in a certain area. The way you can do it is, for instance, so first, of course, build this detector of solar panels to get the exact surface, then estimate the power per unit surface. So here, for instance, for 10 meters square, we know that it's roughly 1600 kilowatts per year. And based on what you detect over your neighborhood, so we did it over Zurich, where we mapped 0.17 kilometers square of solar panels. Then you can estimate the power source, so 27 million kilowatt per year. And so that gives a starting point to, for instance, design the smart grid or have a better information regarding this type of specific energy sources. The same on the swimming pool. So that's a typical one that you will find in cities that you want to map for different reasons. Could be geomarketing, could be audit of tax declaration. There you will first want to detect these swimming pools and then match their localization with parcel address. And then from that, you can either really build on top a dedicated portal for visualization or really just extract this information into any GIS. And so here also you can either localize or find really the exact shape, which can allow to further filter based on the size of the swimming pools, for instance. Mapping all the green parts of the cities, that's something very useful when you want to start to investigate a little bit. All the trees and the green spaces are spread over your city. That's part of the evidence of a sustainable city, how it manages the green spaces. And that's something we've done over Lyon. So to show you here an example. Yep. So this is basically Lyon. And so here, if we look, these are different cells. So when you get outputs and you've run your detector, so you can navigate through the different zones. This is to not load too much your browser. And here you see, so some of the outputs, it's loading the image behind where you have basically all the green spots. Zoom further. Yeah, and these can really be created very quickly and run in 2 clicks. There, the imagery is available over Lyon, so that was extremely easy to plug and play, basically. So, oops, an example also of an application that was built on top of Picterra API. It's Group IT. So this is an initiative from one of the university in the Valais in Switzerland, and in partnership with the IG Group company. What they did is a marketplace where solar panel installers can connect to private people and to make an offer to install solar panels. And so what happens is that you provide your address, and based on the imagery and detectors on Picterra will detect the objects on the roof and then be able to fit solar panels, standard type of solar panels on the roof, and basically really see what is the real potential that you have on your roof, considering really what is already up there on the roof and already existing. And so that was done using our API. So detectors are called to that API, and then everything comes back on that platform. And then there can be this exchange between installer and private people and the tendering process. We have been integrated in the software FME from Save, so a very flexible software where you can build quite complex workflows. So there's the Picterra connector, and where they show this example of crack detections on airport. And in the end, at the end of the workflow, you get basically reports where the different zones ends up with the surface covered of cracks, the total surface in an Excel sheet, and they also directly produce some CityWorks basically job description to be used for maintenance work directly. Finally, I wanted to mention the Pilot City program, which we are part of. These are high school students. They developed projects in class using actually Picterra technology. And the idea is that after they perform this project as part of their summer internship at a city council or an employer. And in the case of the city of Hayward, they are invited to basically use Picterra to map the assets, some of the assets of the city, and they want really to do that to basically increase the efficiency and the automation of what the city is doing. Among the different IDs they want to map, there's the idea of find illegal waste dumps, some fire risks element like dead trees, different type of damages on the roads, on the roofs, and then also some elements that are missing from the cadastre, for instance, bike lanes. So these are the different elements, and the students will start to investigate and then propose these projects to the city. I wanted just to mention here a different type of imagery that can be also used actually. It's digitized maps or cadastres that can be brought on the platform, and you can start to detect certain basically symbols on that and extract some of the pieces of those maps. So let's jump to the demo. So the idea there is to show you a little bit how data is imported on the platform, how you create a detector, either for relocalizing elements or for segmenting purposes. And then I'll show you how this improvement process, how you validate the detector, and finally, how you launch it at large scales over different areas. So let me connect to the platform. So when you just register the platform and you end up on your library of detectors, basically. And from there, the first thing you can do is to load some imagery. So in my image here, you can basically either upload any images you would have or go to online map imagery. And this is where you can either access this Sentinel, this satellite data at 10 meters for free. So you see here, for instance, this is over Lausanne in Switzerland. So that gives you a little bit of a feeling of the type of resolution. So 10 meter, you see that you have something that tells you a little bit where is, of course, the urban part of the city, but you are not really down to the individual buildings. So this is more for change monitoring and basically having this macro view. But then you can connect your own server, as I was mentioning. So here we connect to this city of Hayward. And this you have the server URL, some of the elements to basically connect at the right place. And we can just then end up on that data. And we can either import some portion of it or load the entire city. And this will be seamless. So you see you have really this full coverage here. And so we can just import everything. Here it is up. So it is here. So we'll just move it in the right folder. City of Hayward. And then we go back to our list of detectors. And so here I will show you what I started to do on road markings. So let's have a look at stop signs. Let's say that we want to extract this information of where are the stop signs, and we want to have them basically in the cadastre of the city. So once you are here in your detector, you can, of course, add at any time new imagery that you would like to use to build your detector. So we could actually add the one we just imported before. So we had this one here, and it has been added. And so here we'll have it inside our detector. So you see, this is the full piece we had before. And what we can do, it's basically just start to add some information on that. So we can just start to spot some stop signs. So you see here's one. So what you do is you give to the model some examples. So this is this training button here that gives a zone to train the model. Once you give a zone, you need to really define what you want to the model to detect. So this is the polygon here. You may want to just say, I want to localize that. So you give here a circle just to say that is basically the pattern I want to look at. You would be interested in looking, for instance, at finding the lines precisely. That's what I will show you after. You could do really the outline of the polygon like that, you see. So doing the full line. So the idea is that we will find different number of examples that we will add, and then we could run the detector. So here we see another one. We could just add it. And something that you can do to speed up the process, if it's always the same type of motif, you can actually duplicate it that way. You see up, then you have exactly the same circle. One thing very useful when you have an image like that is that you can loop through the different training areas you have, because you saw that the area we have is huge. So going like that, it just basically loop through. So that's different examples. Training areas that have been given. You see these are empty. They have been set basically to tell the model that there's nothing to detect in these zones. Because at first, it might think that anything that is white on a road is interesting. So you have to basically guide the model like that. Here also, there was some confusion, so we brought these counterexamples on top. And once we train the detector, we'll basically get some outputs in these testing areas in red here. You see these testing areas, they allow you to get some outputs. So you see here we have a big one, and the outputs here can be visualized as centers. We see them as pins, and you see here what it found. So you will see some stop signs, but you will also see that it got some 25 here, for instance. So this means we would have to give a counterexample probably here in order for at the next iteration for it to not misunderstand it. And that's the way you iterate very easily. Once you want to get into some scores and have a way to really see what you are doing in numbers, you have this accuracy button here that allows you to do some accuracy zones. So you will find some other stop signs, and you will basically add a zone on top of that and add an example. And you will do that also on different places. You can put some of these zones where they should find nothing. And in the end, if we loop through, we see basically these accuracy areas. Here, he found one. And here you see that he was confused. He found something that he shouldn't find here. And so basically, and that's why he got this 80% counting precision. And then the shape, in this case, the percentage accuracy of the shape is not very interesting because we only want to localize. That's the way you basically loop through and iterate. And each time you train the detector, it just takes like a minute to get a new output. And once you're ready to go, then you can basically get back to your images and then run the detector on it. I will show you basically here, if we go to City of Hayward, and let's say we want to run it on that image, what you can do actually, if you go to info here on the image, you can define the zone, some zones where you want to do a detection. Let's imagine you had all your city and you want to only run the detections over, for instance, the crossroads, or maybe you have all the layout of the roads, and you don't care to find stop signs on top of roofs, of course. So you could load all your roads and only detect inside this. And so here, that's what we did. So you can upload a detection area like that. And basically, up, let me check. And it will basically define a subzone inside your image. And that's very useful, either to chain different detectors, finding first buildings, then inside buildings, detecting some elements on the roofs, etc., etc. That allows to really reduce the amount of computation that is done when running the detections. And then you can simply run the detections on top of that, and you will end up with an output inside the image. So in this case here, we can visualize what was the output and zoom inside it. And so we see, found the stop signs here. This one was too unmarked, so we couldn't find it. you missed one here, etc. So that's the starting point to really get the data, export it. That may be a way to also then review it for the maintenance. So you can export actually from here by downloading this output as GeoJSON or different type of formats. You can also export only the centers as we have it here now. And you can generate a PDF also that will do a quick report on the statistics over that image. Just to show you something also quite important here when you do the vector, when we did the stop signs, that was really for localization. If we would do something like finding the yellow lines, let me show you that. Here, for instance, we did here, there was a yellow line below. We did a certain number of examples and counter examples. And what we defined here in the settings was that we want to do segmentation. So you have this by default to count, and you can define it as segmentation. And then the output and the rest, you don't have to change it, but this will favorize to have connected elements together. If you put count, it will favor to really separate the different elements. What you can also do, what you saw for the graveyard, for instance, is to set the output type as oriented bounding box. So this box here, and so you will get rectangles that will be oriented over the elements. That is very useful when you know that what you're looking at are rectangular shapes. Then the size filter can be useful also to be set. So auto is basically removing too small detections and too big. So based on the average size of what you annotated, you can also define a custom range in meter square to filter out the detections. So this is it for the live demo. I will come back to the presentation, and now we will basically go for the question and answer. I will pass the mic to Monica and Errol for that. And of course, there will be a recording of that webinar. So if you want to go through back again this live demo and be able to put pause along the way, you will be able to do so. Thank you.
All right, so we have a few questions. So first one of you has asked what road defects can I detect using Picterra? So I don't know, for Frank or Errol, would you like to answer that one?
Yeah, so I think for probably what you people understood through the webinar, but I want to emphasize it here again. There's not really a limit, so you saw that it's very flexible. So you could do read the mapping of the cracks, or localization of the intersection, or the potholes, or any actually other elements that may be relevant if it's about finding the root conditions. So there's no limit actually in what you can really detect if it's there in the imagery.
Thanks. The second one, can Picterra API be integrated into web or mobile apps? I think the answer is already there.
Yes, definitely. And I invite everyone to have a look at our API. We have a Python library that you can have a look at, and feel free to try to integrate that in your workflow. If
you're not sure where to find it, and if you're interested, just drop us a line and we will send you a link. Another question is what accuracy can be achieved using Picterra detectors?
Yes, so there you saw in the live demo, or you could basically measure the accuracy, but in terms of limitation, the accuracy, this is mainly basically linked to the amount of training examples you will provide. So that's why usually we recommend to start with not too much data, see what you get as output. Is that accuracy enough? And otherwise you continue to bring more data. And so you are sure that you are not bringing too much. and then depending on what you try to extract, there might be the need for more data, and the accuracy might be more limited. So if you have a lot of very similar elements that you try to distinguish, so the complexity of the background, this will limit basically the accuracy you can reach.
And this is also a question that is asked pretty frequently, is could Picterra be used at the edge or offline?
So yeah, that's something that comes back, and something that we wanted to have a way to answer to that. So basically what can be done is that the training part of the detectors, as you saw it on the demo, is something you really do on the platform. But once a detector is trained and wants to be really run in production, it can be actually exported as a Docker container and integrated in your own infrastructure on your own machines. And so this is part of actually our new enterprise plan. So that's also something you just reach us and drop us a line to know more about that.
And the last question that we have on the presentation is how can AI help to build sustainable cities? Aro, I think, would you like to answer that one?
It's a good question, and sustainable cities are a subject in and of themselves, but AI is already being used to build design, new developments all the time. There are a couple of very specific examples I can give you in how that is. For example, with autonomous motors, autonomous cars, vehicles, trucks, transport. There's plans in the works for all of this stuff. Autonomous vehicles and mobility work on AI. The way that you map and monitor traffic, there's quite a lot of machine learning in that in order to plan and sort of dynamically allocate priority to routes at given times. Even things like collecting the rubbish. The machine learning has been used in conjunction with IoT for that. Where to put bins and how to collect them in the best possible routes to minimize the amount of wasted time. AI is a concept, so let's be quite specific. Machine learning, deep learning, predictive analytics, all of these things are used in connection with IoT on a number of different scenarios. There's a company in Norway, I believe, which designs and spends a lot of time building the perfect building sites, so that there are billions, literally billions of different characteristics and factors that you may want to take into account when you're looking to build a development. So things like runoff, solar flux, wind direction, access plans, all of this stuff can be a part and parcel of building the perfect sustainable development. And finally, it's not a particularly pleasant subject, but even things like sewage management, the amount of chemical you need at given times for given events and given conditions. They use machine learning to plan and develop a process for that, so that you're not constantly pumping chemical into the water if you don't need to, or you do the bare minimum to do what's required. So AI is already being used to build and manage sustainable cities, and it's only going to grow. It's going to be in every aspect of architectural and developmental processes, and it will become more and more a standard part of how we do these things.
Excellent.
Thanks, Aro.
I think we can close it here.
Yeah, so we've got more questions on chat, but because we are running out of time, maybe we will answer them later. We also promised an ebook to everyone who participated, who registered. So we will take a look at the questions, answer them, and you will all receive answers. I hope it's fine.
Excellent. So thanks everyone to have attended. It was very really nice to catch up in this beginning of the year, and but definitely stay safe. I hope you are all doing not too badly in this confinement situation, and looking forward connecting soon with you.